back in 2007 in preparation. And there was this very nice graph of what should happen as a function of photon energy. And you could pick out what would happen for these three target energies. This was done for the specs that they told us at the time. They didn't tell us that we could change the pulse duration, right? But all these things happen as you go. And so if you actually plot what's going on from the theory in terms of a visual as opposed to those lines, what you see is that at 800 eV you're below the threshold. So the only thing that you can actually talk to are the valence electrons. And so you go.
Could you just explain what APV means?
Ah, yes, I can do that. Okay, V are valence electrons. P are photoionization electrons from inner shell. A is an Auger electron. So when you're below the threshold for 1s excitation, the only thing you can talk to are the outer electrons in your neon atom. But what you can do is, because you have so much fluence and so much flux, you can take off all of them, right? And then if you go to this intermediate energy, 1050, you can go through this sequence where you have first a photoionization, and then without doing anything, you have an Auger decay. So you get two charges for one. And then you go photoionization, Auger decay, so on and so forth. And then if you go to very high energies, 2000 eV, you're above the ionization thresholds for every single charge state of neon, and so you can strip everything. So those were the three energies that we picked. And actually, when you go to these X-ray sources, you can't actually, it's not like going into your lab where you can go back and improve, right? You can't, you only have so much, you have your 5 days, and that's like it. Okay, so that's all about charge states, but you might like to know how you got there. And so you can actually figure out how you got there by doing some electron spectroscopy. So at low intensities, you might imagine this scenario where you first do a photoionization, then the Auger decay happens, taking one hole in the inner shell to produce two holes in the outer shell. And then followed by another photoionization, this PAP. But at high intensities, you can imagine the situation where before the Auger decay happens, you've actually taken out another inner shell electron to form a hollow atom. And so then you can imagine the same other scenario. But it turns out that if you look at the Auger electron that goes into a double core state relative to one that goes into a single core state, they have very different energetics, so you can easily distinguish them. And so the actual apparatus that was used for this is shown here. So we have a number of time-of-flight electron spectrometers that will give you angular distribution from which you can distinguish a photoelectron from an Auger electron. There's a little neon gas jet, and also an ion time-of-flight spectrometer. And the X-rays would come in, and they'd be focused down to a micron or so, and we would just look at what happened in here. Very simple. This was really put together by John Bozak and Christoph Hostad of the LCLS. So in day one, we had these really interesting observations, right? Well, the first thing we found out was that when you have a single 100 femtosecond X-ray pulse at that very high photon energy, you fully strip the neon. And so you can make hypergenic neon, see? And it's a 6 photon, 10 electron process through this, PA, so on and so forth. The other thing we found out was, you can actually change the pulse duration. And what we found out was that if you have shorter pulses with equal pulse energy and fluids, you suppress the absorption and the damage. Now this is really weird because usually, if you have a shorter pulse, it's much higher intensity. And usually that causes more damage, but not so in this case. And what we were doing is we were changing things between like 80 and 300 femtoseconds. And those are really weird numbers because I already told you that the Auger decay happened in like 2 femtoseconds. So we were quite confused. We did not know what was going on. But on the other hand, we also,
I'm just wondering, what do you mean by damage?
Well, by damage, what I mean is more ionization. So damage, so yes. So if something is not in its original state, we consider it damaged. And so if you have more if you have an abundance of high charge states, then it's more damaged than if you have a lower abundance. And so what we would see is with the longer pulse, the red, you have much more high charge states than with the shorter pulse at 80 femtoseconds, which is black. So we'd say, okay, we've got more damage.
what are the time peaks? Does each peak and like a time peak in front of it?
There are isotopes that.
Oh, I see.
So, I told you about the rate equation model. It actually works very well, and because you only have a limited amount of time, you just have to march through and do what you did. So we did our three energies, 800, 1,000, 50, and 2,000 eV, and found, basically that the rate equation model worked reasonably well to explain what was going on. So we thought, okay, well, this is good. I mean, but we really wanted to go back and understand what was going on with that pulse duration dependence. And so it always turns out that when you go back and think later, then things become more clear. And they even become obvious, but they weren't obvious at the time. And so what happens is that, basically X-ray absorption is due to the presence of, at these energies of 1s electrons. We're out at 2,000 eV now. And that when you have high X-ray intensities, you eject those 1s electrons. So there's no more absorption that's going to happen, right? And that explains in general what happens. But what about this weirdo time scale that we were talking about, 80 to whatever, 300 femtoseconds? Well, it turns out that the Auger rate changes dramatically when you go up to higher charge states, because there just aren't as many electrons out in the outer shells to actually do the Auger. And so when you come out to charge state 7 or so, now the Auger rate, instead of being a couple femtoseconds, is now on the order of 30, 40 femtoseconds. So now you can actually see why changing the pulse duration between 80 and 300 actually makes some kind of difference. And it's because it takes a long time for those Auger electrons to fill back in to any type of hole, such that you can actually continue on with your recycling process. And so we also use the electron spectrometers to track the ionization mechanism. And in particular, it was very useful because you could really isolate how many double core holes that you had made. If you actually, Auger electrons are isotropic, photoelectrons you have some direction that you know about. So if you go to a 90-degree geometry where the photoelectrons tend not to be coming so much, and you look at these high-energy Auger electrons, you can actually find a very clean signature of a hollow atom production. That's this double core hole Auger yield compared to the single core. And it turns out that the amount of this Auger yield that you have is huge. So we're making like 10% of these hollow atoms compared to what you might see at a synchrotron, which is just due to electron correlation of less than 1%. And this is very, it's interesting because then it also gives you some measure of the nominal electron pulse duration because you can calculate what it should be. But then we were kind of interested, well, okay, then what happens, if you've made all these hollow atoms, what's that going to do to all this scattering and all, this whole coherent diffractive imaging business, right? Is that going to do something bad? Turns out, not so bad, right? If you take a look at the ratio of the absorption to the elastic scattering, say AKB, where you might actually want to do one of these things, turns out that for the normal situation, for the normal carbon, that ratio is 20, and for the hollow, it's only 2. So, it doesn't damage as much. And then if you actually do a calculation of the form factors and whatnot, the biological guys are really only interested in resolutions to around 3 angstroms or so. And the actual decrease in the scattering out to that, that Q is not that much, even if it's hollow. So it's not so bad.
Linda, what precisely do you mean by elastic scattering? Are you referring to Rayleigh scattering?
Yeah, Rayleigh scattering.
I see.
Yeah. So so that paper, with saying kiloon, it's like, oh well, this could be bad, and so that was sort of the start of the whole package to just calculate what's going on, with atoms in these fields. And so this was actually published in Pierre's least favorite journal, but I want to say we had a lot of collaborators on this, because it certainly wasn't just us at Argonne. Okay, so these are the things that we learned. That the sequential single photon absorption that I showed you the picture of, that really dominates the interaction mechanisms. It turns out direct 2-photon absorption is small, and we'll talk about it a little bit later. This X-ray-induced transparency has also been called frustrated absorption by Nora in her paper, but it's really a general phenomenon. It's been seen in molecules. This is Nora's paper. In clusters, this is one of Christoph's papers. In solids, by a whole bunch of people. And, the implications for imaging, it's not so bad. And also, of course, AMO is always good to have as a diagnostic of what's going on with your laser. So, what I want to say is it's a big team effort. It's not just the folks at Argonne, including Robin Sanford, who at the time was there, as a theorist, but it's also, all these guys who are actually in the control room, who are running things, right? Because they don't really like you to go into their hutches, and so, because they know what's going on better than you, because you're only there for 5 days, right? And then out at the, at the Accelerated Control Center, the MCC, the main control center, they're real heroes, because, you can't, the LCLS has fixed gap undulators, so you can't actually change the energy like you can at a synchrotron however much you want. You actually have to call them on the phone and tell them, change the energy to whatever, 800 eV. So then they have to change the electron energy in the entire linac to get you to change, for you to change your, photon energy. So, they were certainly heroes. Okay, so now let's look at a few of these other weirdo things that AMO folks love from optical vision. So there's this, what's going on with this non-sequential double ionization? So in optical wavelengths, there's this very famous, maybe this is not the right one because it's not really like that, but there's this very famous paper which shows precision measurement of strong field double ionization of helium. And it shows that for the double ionization of helium, there's this big non-sequential mean that, at 10 to the 15 watts per square centimeter is like 10 to the 6 times greater than this sequential business that we've been talking about. So it's very natural to think, oh, well, shouldn't we be able to see some of this in the X-ray regime? And, it's been so fruitful in the optical regime, there must be something good, right? But it turns out that it's very, very hard to see. And in fact, of course we looked for it, in the initial experiment, because you could have two 800 EV photons, right, clearly making, a double ionization, but that wasn't what happened. It was, certainly swamped by everything. And so it was only seen by looking at helium like neon, in fact. And this was, a paper by Gilles Duy, who's now at Argonne, with Lou DeMauro leading it. And so what you can see is that, a signature of this nonlinear absorption is that you would have a quadratic dependence of the yield as a function of the intensity. And so when you went below the threshold for production of this neon 9+, what you would see is that below threshold you could see this quadratic dependence, whereas above threshold the production of neon plus would be linear. And it turns out that, of course, there's more than one way that you can actually come to it, because it's pretty complex. You can have the normal 2-photon direct ionization if you start with neon 8+ here. But you can also come in this other way, where because the Auger lifetime of the neon 7+ was so long, you stay in this excited state, and you can ionize out from an excited state and get to the neon 9+ also. So there are these two ways that actually contribute to this quadratic dependence. And the magnitude of this that was observed was 10 to the 3 larger than predicted by perturbation theory. So this is a sign, right, that it's hard to see. And the value of this 2-photon cross-section was really enhanced because it was near, there was a resonance that was fairly nearby. And, of course, this importance of hidden resonance should be emphasized to some degree, because if you're changing, if you're going from 0 to 10+ in 100 femtoseconds, there are resonances all over the place, right? And so what happens is that, this high fluence pulse is altering the target, and there are these enormous hidden resonances which are way higher than the background. So here you can see resonances for 1s to 2p and the 1+, 2+, and 3+, ion stage. So if you happen to sit your energy, your photon energy on one of those, you can do all kinds of damage. But what about something more complex than neon? Okay, so there's much more going on, right? So neon is pretty simple, right? you eject a 1s electron, and you can have this nice OJ decay. But if you, for example, take xenon, you have 54 electrons. You eject a 2s electron, and then you have this huge cascade. And this cascade, so instead of just having one electron come off at it, you have 1, 2, 3, 4, 5, 6, 7, 8 more electrons. One photon, 8 electrons, is really complicated. How are you going to deal with this? Well, it's a computational challenge, and one that was solved by Sankil Sun and Robin Sandford at CFEL. But again, you can use these, simple, cross-section perturbative models. What you see is that here's this pulse. It's an 85% pulse. It's got a lot of energy in it, more than 10 to the 12 in a square micron. And here's the pulse. And so you start out, you have photoionization that causes all these OJs. And then eventually, when you get up to higher charge states, you can start to have fluorescence because it comes into play. But if you can saturate out, then you can get all the way up to the xenon 44 plus with this one thing. But the total number of electron configurations is huge, and so the Monte Carlo technique was used to do that. So that was followed by an experiment at SACLA, done by Kiyoshi Ueda and his group. And here, the X-rays from SACLA were 5.5 keV, but instead of having such a huge fluids, they had slightly smaller fluids. And so they couldn't actually saturate all the way out, but they still got out to 25 or so charge states. So it's all in one pulse. You can see what happens: photoionization followed by OJs and so on and so forth. Now, if you take xenon, and instead of looking up at 5 keV, and you come down to 2 keV, you can also see many things that will happen. So you can still crack open this M shell, and what you can see is that you can have, single photon, 2 photon, 3, 4, 5, 6 photon absorptions. This gets you all the way up to 28 plus. And the slope gives you the number of photons required. And all this happens in, a few femtoseconds. What I want to show you is that this whole creation in xenon is on the same time scale, and all these OJ decays are on the same time scale as the XFEL pulse. So you create this 3D hole, and within a femtosecond, it's making all these 4D holes to 2 plus, 3 plus, and it just cascades down. It's enormously complex. And we haven't even talked about resonances. So what about resonances, right? So it turns out that, the initial model was that, okay, you're sort of in a saturation mode. You're going to ionize all the way up where you can do 1 photon ionization, then you're going to quit. And that's your end charge state if you have enough fluids. But it turns out that when you take a look at these more complex atoms, that's not exactly what happened. So at Argonne, when you had 480 V, the sequential single photon limit was 10 plus, but they observed 13 plus. And in xenon, at 1500 EVs, this limit was 27 plus, but 36 plus, right? That's a pretty big difference. But when they were at 2000 EV, everything worked properly. So kind of like, oh, that's really an odd thing. And this was led by Artem Rudenko and Daniel Wallace, and was published in another bad journal. but what it showed was that simple X-atom model actually did not work to predict what was going on. And the reason was they hadn't really included resonances. And this is the computational model that is housed at CFEL. But as I told you, they use very, very simple calculations for all of these quantum mechanical cross sections and whatnot. And so what we thought is that it would be a nice contribution if we could actually take into account all those resonances. And so this is something that Fei Ho and our group did just recently. And it's a huge challenge because of the number of electronic configurations associated with all possible bound-bound transitions in the atom. So here, for Argonne, it's not so bad. Without these resonant excitations, the number of electron configurations that you might want to consider is manageable. And when you get up to xenon, with these resonant excitations, you're getting up to like a mole of electron configurations that you have to consider. And the maximum number of an unsigned 64-bit integer, say, points out to me, is less than that number. And so you can't just make a big table and then pick out what you need when you need it. And so you really had to have a really efficient database for storing and retrieving all this atomic data. And he did that. And so then it turned out that we could predict not only what happened with the anomalous things in xenon, we could actually track what was going on in the Argonne. And so here, what you see is, going out to this Argonne, beyond 10 plus, you can see here is a particular pathway that goes this purple photoionization, Auger, photoionization, Auger, so on and so forth. Out here, you have this one little channel that's a resonant excitation when you get way out into these higher charge states. That actually accounts for about 25% of the yield of this particular charge state.
So what's I'm sorry, what's on the vertical axis? What are you plotting?
Well, this is like population.
Okay.
Okay, so this starts out as 1, and so when you get to one of these places, some of these stop, right? And so this is the reason we have this is because I saw Pat Damer do a Sankey diagram of how energy goes in and how it's used. I said, oh, we can use that to display, where all the population goes when you start with, a neutral atom and where it ends up. And so some of it is ending up, for example, Argon 6 plus is red stuff, is some of it got stopped at that particular place. So if you add up all these bars, then you'll add up to 1 on the other end. So anyway, so it's very complex, but you can trace it all. We have a way to trace it all. So we figure, okay, now we know where all the electrons are, at least in this one atom, right? And so we figure, okay, well, this is a building block for all these other things that we want to do. So,
what kind of pulse do you use here?
what kind of pulse do we use here?
Sculptural pulse or the real
Oh, it's a Gaussian pulse. Usually it doesn't make so much difference for these things because, each one of these states lives a long enough time that those little short spikes aren't at the same time scale. But okay, so that was good. And then, we also wanted to investigate what would happen in some of these other situations, and so we made this complex landscape of resonances in these high-phase pulses. This is an example of a krypton. What you see if you pick a particular photon energy, say 2 keV or so, what you do is you first, this is all of them together, but here they're separated out into resonances for core-to-core, core-to-valence, and core-to-Rydberg. And if you pick 2 keV, what you see is you first run into core-to-Rydberg, and then core-to-valence, and then core-to-core, and so on and so forth. So, and what you know from this sort of thing, you can figure out where you can go to minimize damage by choosing your photon energy judiciously. And maybe you didn't really need this to do that, but okay. So let me summarize what basically I said. Okay, so atomic interactions with intense X-rays. Optical strong field interaction is basically a single electron multi-photon interaction, and you strip out one of these outer electrons. But for these ultra-strong X-ray interactions, what's going on basically is you have many single electron, single photon interactions that are in a sort of complex system. And so this is the challenge is to be able to model, I would say, to understand all that in this complex system for other applications. But it's central in these XFL experiments with focused beams. It's predominantly sequential. These sequential things display nonlinearity also, but it can be reasonably well modeled. These photoabsorption simulated emission rates can exceed the rates of these intershell decay processes. Multiphoton absorption in the X-ray regime is a little bit insensitive to the spiky structure of the Sassiapiel pulses. Everything is sort of they're all single photon type processes basically. But there are continuing challenges, which I'll tell you about tomorrow. If you really want to go to these, imaging things, you want to look at the molecules and bigger things. So So in increasing complexity, and of course the real challenge is if you'd actually like to start to control inner shell dynamics, you obviously need better X-ray lasers to do that than what I talked about now. But those are interesting continuing challenges. So I want to, you're supposed to talk to us experimentalists. I want to show you a whole picture of all of us experimentalists at Argonne. This is a picture of the whole group. And I want to point out especially, this is Fei Ho, who did all those calculations I sort of just showed you about. This is Christoph Bosted, who just joined our group from SLAC to become group leader. This is Steve Southworth, who was previously a group leader there. And we had Gilles Denis, who you heard some of. He was previously a nice postdoc with Linda Moore, who led some of the experiments there, and Anne-Marie March, who's really a new star to come. And maybe with that. So thank you for your attention.
I'm chairing you.
X-ray is used transparency. I mean, is it that the cross sections have minimum once you reach a certain ionization stage?
Well, okay. In the example I showed you, basically it's the absence of absorbing electrons that causes the X-ray
So you
transparency.
completely strip the atom?
Well, you strip the atom of the electrons that are doing the absorption. You could still have outer shell
But I
electrons.
thought X-rays absorb everything and ionize anything.
Well, they can, of course, ionize.
But you're saying the outer electrons
Those have a very small
cross-sections.
cross-section at the energy that you're looking at. Like, those might be like 5 kilobarns, and the others are like megabarns or something.
Okay.
Yeah.
So you mentioned that the free electron laser was kind of incoherent. So can you seed it with another X-ray laser to make it more coherent?
You can't, yeah. Actually, I think I have slides on this in maybe my next talk, and Margaret knows a lot about seeding X-ray lasers. Turns out that it's quite hard to seed at wavelength for hard X-ray energies because it's hard to get like an 8 kilovolt seed or something like that to put in. But it turns out that there's this very tricky way that you can actually seed the X-ray laser. Remember I told you how the undulators came in segments? They're like 3-meter segments, and you can slide one out and you can slide something else in. What you can slide in is a little monochromator, a little diamond monochromator, which actually, what it does is it acts as a little it does Bragg reflection at a particular energy, and then what comes out of that is a little monochromatic seed. So if you use like 8 undulators, which makes this ugly spectrum, and then you put in this little filter, basically, then out comes this little monochromatic seed because it's only one energy. And then the electrons, you skate around this little thing, such that the electrons then interact with this little monochromatic seed for the rest of your 90 meters down the undulated line. And in that way, you can actually get seeded hard X-ray pulses. And so that was quite a nice little demonstration, and it works reasonably well. And that was the reason that we wanted to do those calculations, because we wanted to know, oh, what's the difference between these 2 bandwidth pulses? And of course, when you have a smaller bandwidth, you have higher brightness, and maybe more control and whatnot. But there's also, the same scheme works in the soft X-ray range, but it's a trickier optics implementation there. And there are also, well, maybe we should talk about this offline. There are all these different ways that you can do this. In Fermi at Electra, this is a free electron laser in Italy, and they have a cascaded scheme where the first part of the X-ray free electron laser produces one wavelength, and then they can double it with the next part of the FEL. So There are lots of schemes out there, and everybody's working in the same